all the electromagnetic spectrum, and I would like to show that also the hard X-ray part is important. This is my, sorry. This is my talk summary. And essentially what I will do is a brief introduction to this observational scenario, particularly targeted to the next decade, and in particular spanning through the EM and GW facilities. And I will end with describing a fast mission concept for a hard X-ray satellite to be potentially launched in before the mid of next decade. Fast missions means sort of small size satellite, but of course it can host significantly good instrument. This is the relevance of GWM observations in terms of the science. Of course, this is already has been discussed in many occasions. And about after this discovery of the BNS merger GW 170817, essentially it was identified that there was this a list of really key physical questions to be answered, impacting like the cosmology, origin of heavy elements, the equation of state and neutral star, also testing the weak equivalence principle, and also another problem that is inherent to the gravitational wave measurement is the breaking the degeneracy between jet inclination and luminosity distance in the GW parameter estimation. This is important. For this, is important to have the EM counterparts of gravitational waves. In the next decade, we have a predictor scenario already for the GW. I'm particularly emphasizing the ground-based interferometer, and we start from the post 05 that is now foreseen the 05 cycle is foreseen to go beyond the 2030. So it has slightly changed a bit this paradigm, but we consider the post-05 scenario and also the Voyager scenario and advanced LIGO upgrades that are foreseen after 2030, and also Virgo upgrades like Virgo Next, etc. And then we have the era of the Einstein telescope and the era of the Einstein telescope plus Cosmic Explorer that will start in 2035, and also LISA, of course. But essentially what we expect is that in 2035 we will have a sort of game-changing situation in which we will have much more sensitive interferometers, that this will cause an exponential build-up of the number of sources. I think, okay, these are the planned detectors and the situation in terms of strain sensitivity, starting from the advanced LIGO upgrade and the Voyager that will take place maybe around 2030. Of course, there is a lot of activity and different options explored, so it's not very clear the situation as far as I understand. And then we have this game-changing situation in sensitivity for the expected in late 2030, actually after 2035. And okay, this I think we can go further. I think that basically the same situation can happen also for the other facility, the EM facilities that are starting from the IR optical UV. With this, I will not list it by words, but this is an impressive list of new and or already operating facility. Then we have in the radio, SCA, ALMA, and GVLA. And possibly we in the X-rays we could have an extended life fluorescent probes form instead of operations. It is and later in the X-rays we have a Neuatina and possibly Lynx and Antizeus. Um, the situation is especially bright for this IR optical and radio, and for the, but for the X-rays, we will wait. We will have to wait until the second end of 2035 to find some significant. So at the moment we rely, of course, on Einstein probe and swarming. We hope that they will get as longer as we can. Okay, I think okay. After 2030, so we will have expected maybe 100 or 1,000 of GWBNS detection per year up to Z equal 1, thanks to this post of 5 improvement. And the limit distance expected to increase to about 1 gigaparsec for neutron-star merger. And but we must emphasize that for many events, as far as the sensitivity of GW detectors go improve, for many events the bulk will be at far away, and prompt follow-up by optical UV telescope will not be feasible for many of them. So we really need our X-rays to detect the GRB. This is, I think, the concept that also Susanna has expressed in her talk before. And we need it for both detection and localization. This is a quite personalized view of the mission scenario. And this is just to, we have these missions that are already operating. Many of them are nanosats, based on some nanosats. The old friends are here, still here. Most of them, apart from Integral, that is still there, but the data are not downloaded anymore. And we will have some new mission under development, like COSI, Starbart, and we count also EXTP and other in mission design study, like Moonbeam Leap for NASA, and ComCubeS for ESA, that is a fleet of nanosats for Compton telescope. And then we have Theseus starting 2037, still in mission design study. And you see here there is a big hole. I think if you have any ideas of who can do the job in this period, it's welcome. But I didn't find any very good solution. So this is the idea for the Grinta mission, is to cover essentially. It was proposed in the 2021 call of the is a mission call to cover this gap starting from 2031. It didn't work. It was actually shortlisted for the second selection phase, and passed the technical screening of ESA. We had overall a good feedback, and the main when the idea is to propose it again for this run that is starting now. So the main goals are GRB multi-messenger and also service, launched in the mid-2030, possibly in 2034, with a LEO equatorial orbit. And the main feature of this spacecraft is that it has a GRB detector here with a 2,400 square centimeter area, sensitive from 20 to 20 kV to 10 MeV, and the hard X-ray coded mass telescope here that is made with that is capable of faster pointing to the target and localize a source, localize a source um, about 30 arc second for a 10 sigma detection, so 1 arc minute at the limit of detection. And the energy band of this instrument is 5 to 200 kV. It's a consortium. We have 17 European laboratories, 47 researchers in 8 countries. This is a table with the main science goal, comprising, of course, understanding physics of mergers, probe nature of jet and structure in gamma ray burst. We have this gamma ray burst detector that could go do a spectroscopy of burst up to potentially 510 MeV, and then understand physical processes driving the energy transient phenomena for basically not only for the GRB but also for other transient. Understand the physical compact object and characterize the population. So we will use the coded mask instrument to perform surveys as in the hard X-rays. And we remember that from Swift and Integral, we have something like 2,000 sources. Okay, I will go fast as the mission they're talking about. So, okay, I think we can go. This is the payload for the hard X-ray imager, the coded mask instrument. We use these CDT units that have a 1 millimeter pixel resolution. This is a long-term heritage of the CDT that are on Integral and are now available and also flown already on the solar orbiter satellites, so they are flight proven. And then the third, we will have these modules of with the GAG scintillator with the CPM readout, and also this technology is quite flight proven. This is a sketch of the spacecraft. We will have this reorientable sonar panel that will ensure high accessibility to the sky, and the TED. These are the TED module for the GeoBear detector that will cover 8 steradian of the sky simultaneously with a table of performance. The sensitivity with the HXI, the sensitivity starting at 5 kVs around 5 milligram in the 5200 kV, and the angular resolution nominal is 3.8 arc second, which means 30 arc second source location accuracy at 10 sigma. This is the effective area of the HXI, which is around it exceeds 400 square centimeter, and this is the effective area of the TED, the GeoBit detector, that is exceeding approaching 900 square centimeter. This is in detail the coverage of the TED in terms of the polar angle distribution, so the angle from the zenith of the spacecraft, and the sensitivity that is compared to the Fermi GBM, and we have about a factor two number of GRB in terms of then Fermi GBM foreseen. So we again we will detect 90 short GRB per year and long GRB 480 per year, plus other sources. This is based on a study of the real database of Fermi GBM events. Operational concept: we will have 3 modes. Essentially, the active modes are 2. We will have a survey mode in which we observe a region of the sky by the HXI, and we will be waiting for a transient by the TED. Then we will have a fast view once we detect the source, and the follow-up, but also we will have the capability to get an external alert and go to the source immediately with HXI. So we aim at also implementing spacecraft communication, not only via both ground segment, but also via satellite constellations to reduce the delay down to the minute time scale from the alert and the repoint. This is, I think, okay. This is to show that the field of view of the HXI, which is around, is between 400 and as a maximum of 900 square degrees, is well suited to follow up and localize the error region on the gravitational wave detector, starting from the post of 5, also going to the more to the later scenario of gravitational wave detectors. And these are the detection rates that we foresee for the post of 5. We do not consider anymore the first line, but for the post of 5, we get something like 9 plus or minus 4 BNS detection per year, which constitutes about 12% of the total fraction. And this will increase because essentially with the time we will increase the number of detection, and we in the Einstein telescope era we have something like 60 detection per year. Okay, this is a contribution to GRB science. Essentially, we have that almost half of this 90 short GRB that we detect will be detected by HXI in gamma and X-ray down to 5 keV, and we measure the source spectra, and we drive also the multi-wavelength follow-up to get a complete picture of the relativistic jet and the interaction with the environment. Then we have in this post 05 this about 10 detection per year in survey mode, and other 10s to follow up by follow-up with GW senior, and then we can evaluate the fractional BNS able to produce a jet, study jet structure, identify nature of major remnant, etc. And with the 2+3 years mission, we can approach the cosmology measurement with H0 1% level, and also test modified gravity theories. This is the synergies with our facility. Yeah, I think I can leave it, and I'm open to your questions. Thanks.
Thanks a lot, Lorenzo. Is there a very urgent question by somebody, because we are really out of time? All right. Thanks a lot, Lorenzo. Talk to you later.